students, in physics in the section heat, let's see the first experiment you have. This is how to verify Boyle's law. You know Boyle's law, you studied. What is Boyle's law? See, it is a gas law which states that the pressure exerted by gas is inversely proportional to the volume occupied by it. Under two conditions. The temperature should be constant and the mass of that gas must be constant. So basically same amount of gas, same mass of gas. At same temperature, constant temperature, the volume and pressure are inversely proportionate. That means if you give more and more pressure, higher the pressure, volume reduces. We all know that if you compress gas, it takes less volume. If you release the compression, meaning you are reducing the pressure, then it expands, it takes more volume. Volume and pressure are inversely proportionate for a constant volume, constant mass of gas at constant temperature. This is what Boyle has given as Boyle's law. In notations, we write as P is proportionate to 1 over V. To change this proportionate into equal, we put a constant K. Here K is a constant. Cross multiply V, you get PV equals constant. PV, pressure into volume, is a constant. Right? This is what we are going to verify now. Let's see how we are going to verify. Now this is what we call Boyle's apparatus. Right? We call it Boyle's apparatus. When I do the experiment, I will show you how it is fixed. You can see on this side you have a glass tube. On the other side also you have a glass tube. And it is connected by a rubber tube. Right? It's connected by a rubber tube. This end glass tube is closed. Can you see? The other end is open. So this end is closed, this end is open. Which means in this gap, can you see in this gap, there is a mass of gas which is trapped. Why? It's closed here. What is here? This is mercury. Mercury is here all over. From here up to here, it's mercury. So what will happen when you raise this end? The mercury on this side gets compressed. The air column on this side gets compressed. Why? When you raise it, the height increases. When the height increases, pressure increases. Mercury is a very highly dense liquid. So if you take it for a higher distance, if the height of the mercury column increases, it gives that much of pressure. When pressure increases, the air column on this side will get compressed. Basically, the volume will reduce. Right? In the diagram, CD is a glass tube with uniform cross section A. The length of the air column is L. The difference between the mercury levels in AB and CD is H. See, the mercury levels, the difference is H. So basically, this much of extra level of mercury, that's going to give extra pressure in addition to the environmental pressure, atmospheric pressure. This extra height of mercury, that will give pressure. Right? So that's going to be the same pressure level here. You know, in a liquid, at the same levels, right? At the same level, you have a tube like this, right? Let's say you have liquid here. So at the same level, at the same height, pressure has to be same. Right? So see, how would be the pressure here? This would be atmospheric pressure plus the pressure given by this H. Atmospheric pressure plus the pressure given by the extra height of mercury on this side. That's going to be the same pressure at this point. So air pressure is that. Right? And this is what we call L, the height of the air column, L. So when you compress more and more, that means if this H increases, according to Boyle's law, when pressure increases here, volume has to drop here. Look at this again. the volume can be written as V into L. V into L. The volume can be written as V into L. And the pressure can be written as atmospheric pressure plus H. H is this, that much of millimeter mercury or centimeter mercury, whatever. Usually atmospheric pressure is around 760 millimeter mercury, or you can say 76 centimeter mercury. So P into V has to be constant. That means volume is A into L, isn't it? Let's use different notations. Wait, let's call the atmospheric pressure as pi. Okay, A into L. What is A here? A is the cross-sectional area of the tube. Right. So this is pi plus H. We know P into V is constant. P is going to be pi plus H. The volume is going to be A into L. Is constant. Here, A is also constant, right? The cross-sectional area doesn't change for this tube. Since A is also constant, if I take this A to the other side, K over A is going to be a constant. Pi plus H into L. Into L. Is K over A, which I will write it as K dashed. K dash, a new constant. Right, previously I took the constant as K. Now you have divided that by A. A is what? The cross-sectional area of this tube, which is a constant. Then you get a new constant. Let me rearrange this. Pi plus H into L is a constant. So we will rearrange this. You can see. Let's take L to the other side. So you get 1 over L K dash will be pi plus H. Or let me write H first. H plus pi. You know K dash is a constant, pi is a constant. Right? So let me rearrange further. 1 over L equals. Let's take this K dash down. 1 over K dash H plus pi by H. So this is a constant. Let me call it M. Pi by K dash. This is a constant. Let me call it C. Y and X. Those two are the variables. H is what I am going to adjust when I am adjusting the height of that tube. Look at this again. When I am adjusting the height here can be adjusted. You have enough rubber tube here. So if you raise it up or bring it down, this H is going to be adjusted. So that is the independent variable. I can adjust it in my own. It doesn't depend on anything else. So H is the independent variable. We usually take independent variable on the x-axis. And depending on H, Y will differ. Y will change. So Y means this one, L. L is the dependent variable. L depends on H. The dependent variable has to be taken in the y-axis. That's how I have rearranged this formula. Can you see? We get 1 over L in the y-axis, H in the x-axis. These two are constants. You should be able to get a straight line. You should be able to get a straight line. That is what we are going to do in this experiment. Change the H. Each time measure L, find 1 over L and H, draw a graph. As long as you get a straight line graph, that verifies Boyle's law. That confirms volume and pressure are inversely proportionate. Understood? Look at the theory again. Pi plus H into LA. I actually took the A to the other side because A is also constant. Since A is constant, right? So 1 over L, A over K, H, A over K, pi. 1 over L in the y-axis, H in the x-axis, A over K, A over K. One has to be A over K into pi. 1. So you can see M is going to be A over K according to this graph, this equation. C is going to be A over K times pi. So if you want to find the atmospheric pressure, if you want to find the value of pi, you can take the intercept, divide by gradient. This is intercept, gradient. AK gets cancelled, you get pi, which is not part of the Boyle's law. Which is not part of the Boyle's law. Boyle's law, as long as you get a straight line graph, Boyle's law is verified. But we can do some additional calculation here. We can go further, finding the intercept, finding the gradient, divide them. That should give us the atmospheric pressure in millimeter mercury or centimeter mercury. This is what the theory is. Let's see how we are going to do this in the experiment. The apparatus, only two apparatus you need, mainly the Boyle's apparatus, the one I have shown you in the diagram. When we start doing the experiment, we can see the instrument. And a set square. Set square will help you to get the reading correctly, because when you see the instrument, when you see the apparatus only, you will understand the scale is going to be like this and the tube will be like this. So what you see is here, the tube, the mercury level will be here. Behind the tube only scale is going to be there. So behind you have the scale, in front of that you have the tube, within the tube you have the mercury level. So sometimes when you keep the eye level at different levels, you may not get the correct reading, the precise reading may not be obtained. So what we do, we keep a set square there to ensure we don't make a mistake when we get the reading. That's the reason using this set square. When I do the experiment, I will show you how to use a set square to get the reading. Look at the steps. Place Boyle's apparatus vertically. Make sure it's vertical. Make sure it's vertical, because see, suppose if we have kept the instrument, say this is horizontal line. Suppose if you have kept it in an angle like this, then the reading you are getting is this much. This is what is going to be h. So when you write pi plus h, it will be wrong, because you are getting the vertical distance, vertical height. Then the vertical height is going to be something else. See, when you draw the vertical line, this is what the pressure giving height it is going to be. Then if you don't keep it vertically, what you measure as h and what actually the vertical height is will be different. So make sure the Boyle's apparatus is kept vertically. Keep the tube with closed end CD at the center of the apparatus. What is the meaning of that? Right. So this is what I call the closed tube. Keep it somewhere in the middle. That means here this is where 0 is going to be in the scale. It keeps increasing, right? So don't keep it at one end of the scale. Keep it somewhere in the middle and fix it. AB is what we are going to adjust up and down. Keep the tube with closed end at the center of the apparatus and raise the open-ended tube, the other side, AB, as high as possible. Take the maximum height with AB, because what we are going to do, take the maximum height, then you get an H, then bring it to the lowest point, you get another H. You know, we are going to draw a graph. Usually 4 points at least will be required to draw a graph. To improve the precision, we will take 5 points. So take the highest point, take the lowest point, in between you can take 3 points. This is what we are going to do. Measure the mercury levels once it becomes stable. Since when you are taking it, when you are raising it up and down, the mercury levels may not be immediately balancing. It might take a couple of seconds for it to, become stable. So wait until it becomes stable. Use a set square to minimize the reading error. Lower the open-ended tube as low as possible and get the readings. The lowest point. Then keep the tube AB at 3 intermediate points and get the readings. 3 intermediate readings. What is the meaning of reading here? Reading means, come again here, in the scale, you can get the mercury level. If the mercury is here, this is one reading. This will be another reading, the other mercury level. So the difference between mercury levels is going to be H. Right? And since you have fixed this one, this reading already you have got it, and that's always the same. Because CD side, the closed end tube is fixed. You are not moving it. So this reading is fixed. Then the difference between this mercury level and the closed end, that will give you L. So every time, now this you take it at the beginning, every time the new reading you have to take is basically the mercury levels. Where is the mercury level? Where is the mercury level? Get the mercury level readings. The difference between mercury levels will be H. The difference between closed end tab or the end of it and the mercury within that, that will give us the length of air column in that. Right? Calculate the length of L of the air column and the difference H between mercury levels at each instance. Take H as positive when AB is above CD. Look at this. Look at this. If this is your mercury level on this side, when you have mercury level here, take this as positive. Suppose if the mercury level is down here, then take this as negative. H has, you have to give a sign for H, plus minus accordingly you will give it. If a straight line graph is obtained, Boyle's law is verified. Atmospheric pressure can be measured using the gradient and intercept of the graph. See, Boyle's law will be verified with the moment you get a straight line. You go a little beyond that, finding the gradient, finding the intercept, divide it, you can find the atmospheric pressure. This is what the experiment is. Shall we do this experiment and see how we are going to do it? It's very simple, because there is nothing much to arrange. You take the apparatus, just adjust the height, get 5 readings and draw the graph. Such a simple experiment it is. Let's see how we are going to do this. You can see this is the primary instrument here. We call it Boyle's apparatus. To do this experiment, this is the primary instrument or primary apparatus. Apart from that, we need a set square or a triangle ruler to get the readings. When I get the readings, I will show you the usefulness of this. If you can't use this, if you don't get it, even you can use a ruler. I'll show it. Right? You can use a ruler, but ideally a set square will be good. Now let's familiarize with this instrument. Let's understand what are the different parts here. Can you see there is a tube that starts from here. The tube goes all the way up to here. This tube cross section doesn't change. The cross section is equal. Wherever you get the cross section, the cross section is same. Also, can you see from here what we have is mercury. From here up to here. See, when I adjust the height, you can see the mercury level changes. Can you see the mercury? Yes. So what we have done with the mercury here, we have trapped some, see within this gap, we have trapped air in this. The mercury has trapped air. This end is closed end. Can you see? This end is closed. So the air cannot exit from that end. Within this gap, where the mercury finishes and this closed gap, within this gap we have some air. The other end is open. The other end is open. So what we are going to do here, the volume of this air, the air which is trapped within this tube, will be proportional to this length, right? Why? The cross section doesn't change. Cross section doesn't change. So if you measure this length, that will give you the volume, that will be proportional to the volume. So we are going to see how this volume changes, the air volume, the volume of this air, how that changes when we increase and decrease the pressure. How are we going to increase and decrease the pressure? You increase the height of this side. Look at this. You can increase the height. When you increase the height of this, that increases the pressure here. Right? Why? All the weight of this, the mercury, right, will give pressure here. So when you increase the height, the pressure will increase. Suppose if we keep it at this level, you can check the mercury level here and the mercury level here. If you get the difference between these two levels, the height basically, this height, the height of mercury from here to here, would be the measurement of pressure, would be proportionate to the pressure that is exerted on this gas or on this air, the air which is trapped here, right. See, from this point to this point, how much extra mercury we have, the extra height of mercury beyond this point, the extra height of mercury would be the pressure, right, would give the pressure. So, by adjusting that height, I can bring it down further. See, when I bring it down now this is the extra height you have. When I bring it down further, I can bring it here. See, this is the extra height you have. Likewise, you can change the height of this open-ended side. We don't change the height of closed-ended side, we change the height of open-ended side. So, when you change the extra height of mercury, the pressure changes. When the pressure changes, volume of this gas which is trapped here, the gas which is trapped here, that will change. Clear? So, we can take down the H. H is the gap between the two mercury levels. Also, we can take down this L. L is proportionate to the volume. So, we can take H as the pressure because H is proportionate to pressure. Then we can take L as the volume because volume is proportionate to L. Then we can draw the graph H against 1 over L graph. Why? They are inversely proportional. Pressure and volume are inversely proportional. Pressure into volume is a constant. That's what Boyle says. That's what the Boyle's law states about this gas. Right. So, we take H in the y-axis. That will give the pressure. And then we take 1 over L in the x-axis, which is the inverse of volume. Draw the graph. It has to be a straight line going through origin. If we can get a graph like that, then that verifies Boyle's law. Right. So, see how we are going to get the readings, how we are usually to draw a graph, at least 4 points would be enough to draw a graph. We will get 5 readings here. What we will do? We will get the maximum height, we will increase it to the maximum height, that will be 1 reading, maximum height. Bring it to the lowest point, that will be another reading. In between, we will get 3 readings. So, altogether we can have 5 readings. That 5 readings will be sufficient for us to draw the graph. Actually, 2 points are enough to draw a straight line. But getting more points will help us to minimize the error. When we are reading, when we are doing the experiment, there can be errors. So, these errors will be rectified when you take more points to draw the graph. So, usually if you expect a straight line graph, 4 or 5 points would be ideal to draw the graph. Let me take it to the highest point and get the first reading. That is the highest point. Now, you can see the mercury level, one is here, the other one is here. Let us get those 2 readings, the difference will be H. Also, we can measure this point, the height of this point and the height of this mercury, the mercury level, the gap will be L. This is what we are going to do, right. So, how are we going to use a set square or a triangle ruler to get the reading? This is how we do it. See, if you want to get the mercury level here, you have to keep the set square like this, so that this level is leveled with mercury, and this has to be touching the scale surface, see, right. And you have to keep your eye at the same level and get the reading. This is how we get the reading, right. You can use a set square, make sure this side is 90 degree. Also, make sure you have kept the instrument, this scale, and this has to be vertical, right. It has to be vertical. Make sure it's vertical, and then you can get the readings like this. But here, I am going to use a ruler and show the readings like this, not for anything else, right, to show it more clearly to you. To make it more clear to you, we will be using a ruler. But ideally, rather than a ruler, a set square would be better. You can get the readings without the error, right. So, let us get the readings one by one. First, we will get the reading here. Students, you can see this is at 45.4. The mercury level, this one is 45.4. Let me get the reading here. You can see this is at 83.9 centimeter, right. So, we can write those 2. Also, let me get the reading here as well. This is at 60. The closed end of the tube is at 60. Right? Shall we write down these readings? We will name these readings. This open-ended one, we will call it AB. The mercury level at the open-ended side, we will call it AB. The closed end, we will call it CD. So AB, CD, if you subtract it, you can get H. AB minus CD. Also, this is the difference between 60 and CD. 60 is here, CD is here. If you subtract that gap will give me the L. L is going to be the measurement for volume. Since the cross section is constant, right, since the area is constant, if you take the measurement of length, that would be proportionate to volume. That's what we are doing it here, right. So, let us write down all the readings we have got now. The reading for AB we have got is 83.9, that is the open-ended reading, open-ended sites reading, 83.9, and CD we got 45.4, 45.4. So, you know L is 60 minus 45.4, which is 14.6 centimeters, 14.6 centimeters. Now, let us change this, change the setup, get another set of readings now. Now, let us change the open-ended sites height and get another reading. Let me bring it down. I will keep it somewhere here. You can see the mercury levels. See, one level is here, the other one is here. We get the readings. I need to change the height of this closed-ended side, so I do not have to get that reading, that remains at 60. All I have to do is get the reading of 2 mercury levels. Students, you can see this is at 44 centimeter, 44, you can see that. Similarly, the other one here. Students, you can see that is at 72.9 centimeter, 72.9 centimeter. Let us write these readings also. As I mentioned earlier, we will get at least 4 or 5 readings, and ideally 3 readings above this, and we will get 2 readings where this mercury level is below the mercury level in the closed end. Right. So, let us write these values and get another reading after that. The reading for AB we have got 72.9, 72.9, and CD 44. L will be 60 minus 44, which is 16 centimeters, 16 centimeters. That is the second set of reading. Now, again we will change it, get another reading. Right, all together let us try to get 5 readings so that we can get a reliable graph with less error. Let us get another reading now. Now, let us change the height again, we will get another reading. We will bring it to a point like this. Get the readings. See the mercury level here, the CD. You can see that is at 41 centimeters, 41 centimeters. Look at this, sir. I am keeping the bottom side of the ruler here. Students, you can see this is at 54.8 centimeters, 54.8 centimeters. That is the third set of readings we have got. Let us write down those readings as well. Now, AB we have got 54.8. and CD we got 41. So, L will be 60 minus 41, which is 19 centimeters, 19 centimeters. We have got 3 readings. We need to get another 2 readings. This time we will bring it down and get the open sided end. Let us bring the mercury level below the other side mercury level. Let us get another reading like that now. I have already taken 3 readings. I need 2 more readings. Let us get the lowest point reading now. Let us bring it to the lowest point, the possible lowest point. Right, that is the lowest point I can bring. You can see the open-ended side mercury is here. The closed-ended one, it has gone below this level. It is not very clear to you. Can you see when I shake it a little, you can see the mercury level is changing a little bit. Can you see that? Yes. So, this is where the mercury level is. let it become stable. Once the mercury level becomes stable, we'll get the reading. Yes. Now it's stable. Let's get this reading first. This is where the mercury is. This is at 33.5 centimeter, 33.5. The other one is very clear, we can get that easily. Students, now you can see this is at 24.6 centimeters, 24.6 centimeter. That's the lowest possible point I could take that to. Let's write down those readings as well. AB we got 24.6 and CD 33.5. So L will be 60 minus 33.5, which is 26.5, 26.5 centimeters. Let's get one last reading. With 5 readings, we should be able to draw a graph. Let's get one more reading. Let's take one more reading. Having 5 points, we can get a more reliable graph. Let me increase this further. Let's keep it at a point like this. Right. You can see the mercury level here, it's very clear. The other one, when I shake it, you can see the level changes here. See? Right. Let it become stable and then we'll get the reading. Students, you can see, I'll show the mercury level again. Can you see? I'm taking this reading, yeah? This one. Right. So when it stabilizes, the reading I'm getting is 37.2 centimeters. 37.2 centimeters. Similarly, the other one, is at 36.1 centimeters, 36.1 centimeter. As I mentioned earlier, actually this is not how you should get the reading. You have to use a set square or triangle ruler, keep it like this and get the reading. But for it to see clearly, I'm using a ruler, normal ruler and getting the readings, right? So let's write down this 5th reading as well and then see what calculations and graph we have to draw to get the, to verify the Boyle's law. Now AB we have got 54.8 and CD we got 41. So L will be 60 minus 41, which is 19 centimeters, 19 centimeters. We have got 3, good, we have got 5 readings. As I told you earlier, as I mentioned earlier, H, that means compared to the closed side mercury level, open side mercury level, how much extra height it has will be an indication of pressure. Plus, the volume is given by L. How? Since the cross section is constant, you can say L is proportionate to V. Otherwise, it has to be cross section into length. Since cross section is constant, the gas volume is proportionate to L. So what we are going to say, pressure and volume are inversely proportionate, which means H and L are inversely proportionate. So you take H in the y-axis, 1 over L in the x-axis, 1 over L, because inverse proportional. So take inverse of it, 1 over L in the x-axis, draw the graph with these points. We should be able to get a straight line that goes through origin. Now let's draw the graph and see whether we can get a straight line. If we get a straight line, the Boyle's law is verified. Let's see whether we are getting it. You can see all the readings that I have got. I have put it into a table here. Let's calculate H and 1 over L for each instance. Let's finish H first. 4583. That will be 38.5, is it? 72.9 and 44. 28.9. 54.8 and 41. 24.6 and 33.5. This is where we said AB is lower than CD, so it has to be minus. Minus, how much is that? 11.1 minus, is it? No. 5, 6, 9, 12, 8. And this is also minus minus 1.1. We have 2 minus readings and 3 plus readings for H. And 1 over L, we have L readings 14.6, 16, 19. One by one we are going to calculate 1 over L. 14.6, 1 over 14.6 will be 0.068. 0.068. 1 over 16 will be 0.063. Next one, 1 over 19 will be 0. Next one, 1 over 26.5, that is 0.038. The last one, 1 over 22.8 is 0.044. If you want, you can multiply this by 100 and make it as 6.8, 6.3 likewise as well. Basically taking these as meters, then you will get like 1 decimal points. But keeping everything in centimeter will have less complications. Now we are going to draw the graph. This is going to be in the x-axis. This is going to be in the y-axis. Shall we see how to draw the graph for this? Right. First, let's plan the axis. We have to plan the axis. See, x-axis goes from minus 1.1 or minus 8.9 to 38.5. So let's take minus 10 to plus 40. Minus 10 to plus 40. Let's see how we can plan the scale. Also, if you look at y-axis, 3.8, 6.8. 3.8, 0.038 is the minimum. 0.068 is the maximum. We have to plan it now. Let me take the y-axis. Let me take this point as the start. This point as the start. Keep counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Up to here I can take 20. Right? So we'll start from 38 to 68 is what I want, right? Let's start from 30 and finish it at 70. So let it be 0.03. Right. Every scale will take it as 0.002. Then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That will be 0.040. 1, 2, 3, 4, 5. 0.050. 2, 3, 4, 5. 0.060. 2, 3, 4, 5. 0.070. Now the x-axis. X-axis we have from minus 10 to 40. Minus 10 to 40. Let's see in the plus side. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we'll take it like this. This is where we'll take 0, 2, 4, 6, 8, 2, 4, 6, 8, 10. We'll take it as 20. 2, 4, 6, 8, 10. This will be 40. So in between 2, 4, 5 will be 10. 2, 4, 5 will be 30. And a minus 10 is required. 2, 4, 5. This will be minus 10. Name the axis. Name the axis. This is going to be H in centimeters. And this will be 1 over L centimeter minus 1. 1 over L centimeter minus 1. Mark the points one by one. First one, 38.5, 68. 38.5, 30, 32, 34, 36, 38. Just after this line, 38.5 and 0.064. 68, 68, 6, 62, 64, 68 here. 62, 64, 68 must be this point. Just after, see, this is where 38 is. We have 38.5. So just after 38 at 64. Next one, 28.9, 63. 28.9. So that's 29 almost. 22, 24, 26, 28.9. Somewhere in the middle in between these two. And 63. Here is it? No, in the next one. Check that. 62, 64, 63 in the middle. 28.9 is almost at 29. In between 28 and 30. Next. 13.8, 53. 13.8, 10, 12, 14. 13.8 is very close to 14. And 53, is it? 53. 52, 53. 14, 53. 14, 53. And the next one, minus 8.9 and 38. Minus 8.9 and 38. Here. And the last one, minus 1.1, 0.044. 1.144. 1.144. Those are the 5 points that we get. Let's see how we can draw a straight line. Obviously, when you do an experiment, you can't expect all the points to fall on the same straight line because experiment will have experimental errors. So practically, when you're doing an experiment, if you get all the points falling on the same straight line, it's a miracle. It never happens. In theory, yes, but practically it won't. So we have to draw the line of best fit with all these points, whichever the line that covers most of these points, that goes close to all these points have to be drawn. Let's see. I think a line like this could be the line of best fit. Can you see? Only this point is an exception. Let me check that point again. That point is 38.5, 68. Check that again. 38.5 is here. 68. Oh, we made a mistake. 62, 64, 66, 68. The point should have been here. We made a mistake. We'll draw it again. 38.5, 38, 38.5, 68 has to be here. Right. Now let's draw the line of best fit. I think that is fairly a good line. That's fairly a good line. You can see that it goes close to most of the points. A little bit of deviation is here between a couple of points. That's fine. Little bit of deviation is acceptable. This is the line of best fit. So you can say the graph is almost a straight line. Since the graph is almost a straight line, we can say the Boyle's law is verified. Right? Don't worry too much about the deviations. Anyway, when you are doing experiments, even when they give the points in the exam, when they say where these points were taken from an experiment, you will never get them exactly on a straight line. Experiment will have its practical errors. So there will be little bit of deviations for each of it. But if you have significant deviation, it can't happen. Say your line is here. Suppose you have a point here, then that is wrong. You have made a huge mistake. That is not possible. But small deviation is always happening. Yeah. So Boyle's law is verified with this. Now, you remember I told you we can take the intercept, we can take the gradient and find out the atmospheric pressure. Let's see how we are going to find the atmospheric pressure. I need the intercept. Intercept here you can see that is at 44, isn't it? That is 0 point, no, not 0 point. 0.044 is the intercept. Let's take the gradient. Let me take these 2 points. Let me take these 2 points to find the gradient. Yeah. I need delta y and delta x to draw the gradient. Delta y and delta x. Let's see, the delta x is 0 and this is 28. 28. Delta y is, this is at 0.062. We'll write it 0.062 minus 0.044. The answer you are getting for that is 18.018. So gradient is going to be 0.018 divided by 28. That is, even if you multiply by 1000, it's going to be 18. 18 by 28 means 9 by 14. 9 by 14. 9 by 14 will be 0.684. Then 6 by 14, 3 by 7, 4. That's the gradient we are getting. Gradient 0.64 into 10 to the power minus 3. C is 0.044. So I can say atmospheric pressure. You remember we studied C over M, intercept over gradient. Intercept is 44 into 10 to the power minus 3. This is 0.064 into 10 to the power minus 3. So you get 44 by 64. That is 440 over 64. You get 6, 24, 38. Then you have 56, 9, 3, approximately 69. Approximately 69 centimeter mercury is the atmospheric pressure we are getting according to this graph. Approximately 69. Look at the process again. What did I do? I found the gradient. Gradient here we got. The gradient we got. You can see again. This was 62. And this was at 44. Right? 62, 44. You get a difference of 18. 18. And y difference 0 here. This is at 28. So 18 divided by 28. The answer we got 18 divided by 28 means 9 divided by 14. 9 divided by 14. So 9 divided by 14. You get 684. 60 you get 4. That is 56. 0.64 into 10 to the power minus 3. C is at 0.44. So 0.44 into 10 to the power minus 3. 64 into 10 to the power minus 3. Both 10 to the power minus 3 is cancelled. 44 by 0.64. I multiplied up and down by 100. 4,464. 6, 6, 4, 24, 38. Then here you have 56, another 0. That's approximately 9. Approximately 9. 69 centimeter mercury is the approximate pressure we are getting for this, the atmospheric pressure. What we theoretically study is around 76 or 75, but based on the calculations we have got here, 69 centimeter is the atmospheric pressure. Clear? Right. So that's a very simple experiment. This is how the calculations we do on that. Now, having noted all these, let's see couple of past paper questions that have come on this experiment. Let's see how we can answer the past paper questions on this. The first past paper question we have, it's a very old one, 1980 advanced level paper. They have given a J tube. The diagram shows a J tube with mercury. If sufficient amount of mercury is available, this apparatus can be used to verify Boyle's law. Right? J tube is a different tube. Right? We have a Boyle's apparatus and a J tube. Right? J tube we usually use to change the temperature. What we can do, this air column, if I want to heat it, then I can submerge this in a hot water bath. Then the temperature will go up, right? So that is where we use usually J tube. Still, J tube and the Boyle's apparatus, more or less conceptually it's the same. So I can still use the same apparatus, J tube, also to measure or to verify Boyle's law. Only thing is there is no scale, so I have to manually find it. If the Boyle's apparatus, it's with the scale and everything, it's easy for us to measure. State the Boyle's law. What's the Boyle's law? The volume of a constant mass of gas is proportional to the pressure at constant temperature. So you have to mention somewhere constant mass and constant temperature has to come in, and then is inversely proportional. Is inversely proportional. Inversely proportional to the pressure of its constant temperature. Obtain the necessary principles to verify Boyle's law using the above apparatus. See, if I redraw the apparatus, this is how they have it. Let me redraw it. This is how they have given you the J tube. Here this is the mercury level, this is the mercury level, H. So you understand the pressure here, right? Pressure at this point, that is the same here. Pressure that will be, if I say the atmospheric pressure is A millimeter, or we'll use pi itself, it's easy. Pi millimeter mercury, and this is H in millimeters. So that's what the pressure is. That much of millimeter mercury is the pressure. And volume here, if I take the cross-sectional area as A, and if this height is L, volume is A into L, right? So you know PV is constant, P pi plus H, AL volume is constant. So you take it to the other side. K over A 1 over L will be equal to 5 plus H. 1 over L equals A over K times H, A over K times pi. Y equals M X plus C. This is what they call the principle of this experiment. Yeah. Next, why isn't it possible to use another liquid instead of mercury in this experiment? Why can't we use another liquid? Why does it have to be mercury? Several reasons are there. One main reason, one important reason here why we can't use another liquid. See, the density of liquid, the density of mercury is so high. So even if mercury is at a height of 5 centimeter, the weight of that is so high because of high density. So it gives a very good pressure, very high pressure it gives. If you look at this difference, see, for a small difference, it will give a lot of pressure here. It's easy to do the experiment. Right? If you want to increase the pressure by 10 centimeter mercury, basically you have to have only 10 centimeter mercury on the other side. Instead of mercury, if we use water or any other liquid, the density of those liquids are going to be much less than mercury. So if you want to increase the pressure is usually measured in millimeter mercuries, right, or centimeter mercuries. Let's say you want to increase the pressure to this air by 10 millimeter mercury, then you have to have a very lengthy liquid column on the other side. Very high liquid column because of low density for other liquids. Right? So you need to have a very long tube to do this experiment. So it's practically difficult having a very long tube and then using a lot of liquid in that to increase the pressure. That's why mainly we prefer mercury to do this experiment. And there are a couple of other reasons as well. What? Mercury doesn't wet the glass. It doesn't stick to the glass. Right? So when you're adjusting the height and all, it collects everything together in one column. It doesn't stick on the walls of this glass tube. Right? So there are some other liquids, sometimes it mixes with air, it reacts with air. Whereas mercury doesn't react with air. It doesn't harm the rubber tube because in J tube it's all glass, but in the Boyle's apparatus it's a rubber tube. Some liquids will harm rubber tube, they will react with rubber. So all those problems are not there with mercury. But main advantage of mercury, high density with small height itself, we can give significant pressure. Let's write it. Mercury has high density. Therefore, with small height, high pressure can be given. Other liquids with low density will need very long tube to increase the pressure significantly. Basically 10 centimeter height of mercury, 10 centimeter height of water, how much of pressure they are going to give? Mercury will give significantly bigger pressure, higher pressure than same height of any other liquid. This is why we prefer mercury as the main reason here. Next, what are the measurements that you will take in the experiment? You saw the experiment when we did, right? The height h, that basically the mercury levels difference, and the air column's length. Let's say difference between mercury levels, let it be H. The length of air column, let it be L. Those are the two readings mainly. Yes. Next, what graph would you draw? You already saw that. Y-axis, we will take 1 over L. In the x-axis, we will take H. That's the graph we draw. 1 over L versus H. 1 over L versus H. If you write it the other way around, if you say H in the y-axis, 1 over L in the x-axis, wrong, because dependent, independent variable. Which one do we change? H is what we change. And 1 over L changes accordingly. So, dependent variable is 1 over L. That has to come in the y-axis. Next. The length of air column trapped in the J tube is 10 cm at an atmospheric pressure 76 cm mercury. What will be the length of the air column if the pressure on the air column is increased until the difference between the two mercury levels is 2 cm? Now look at this. PV is constant. P1 V1 equals P2 V2. P1 atmospheric pressure 76 cm. V1, they say the air column's length is 10 cm. 10 into A. A is the cross-sectional area. P2, the difference in mercury is 2 cm. That means with atmospheric pressure, another 2 cm of mercury pressure is also going to be there. Then it will be 78 into V2. Volume is what they are asking, right? What will be the length of the air column? So let's say L into A. Cross-sectional area doesn't change, so both sides A gets cancelled. A gets cancelled. L will be 760 divided by 78. 380, 39. 380 divided by 39. 9, 81, 8, 36. Is it? No, 27, 8, 35. 290. You get 7, 63, 7, 3, 21, 27. You get 9.7 centimeters. 9.7 centimeter. When the column difference is 2 centimeters. Yeah, when it is 2 centimeter, you get 9. Earlier it was 10 centimeter, the length of the air column. Now when extra pressure is given, that is compressed. That is compressed. Suppose you got an answer above 10 centimeter, then you are wrong. Because now we are giving more pressure. More pressure means volume has to be lower. It's 9.7 centimeters. That's all in that paper. Now we'll see another one. The following year, 1981, we have another question on the same concept. PV equals constant. Boyle's law, same. An air column is trapped in a plastic cylinder with tight piston. The bottom end of the cylinder is sealed to prevent airflow and is kept on a balance as shown in the diagram. So this is like a kitchen balance or the table balance. When the piston P is pushed downwards with hands, it freely moves downwards and compresses the trapped air. Okay, so this is a piston setup, right? You can press it, right? When you are pressing it, the air here, right? This is where the air is. That gets more compressed. So it gets more pressure, and the volume reduces. How they are going to measure the pressure here? When we are pressing from up, you can read the reading, like how much pressure we are giving, how much force we are giving. You can read from here. It will show you mass. So mg, suppose if it shows like 2 kilogram, let's say it shows 2 kilogram, then I know I'm giving 20 Newton if g is 10. Then how do I find the pressure? Pressure has to be this atmospheric pressure plus whatever the force I have given divided by area. Area means the area of this one, cross-sectional area. Because force divided by area is what you call pressure. right? Atmospheric pressure is already there, plus additional force you are giving, that additional force divided by the area exerted, the force exerting area is what you call pressure. This will be the pressure. So F, what you get? mg. M you can read from the balance. G is considered to be 10. Usually in the exams they give it on the front sheet. You will have assume G to be 10 or 9.8. Whatever they give, you have to take it. A has to be given. Let's see how whether they give it. Compresses the trapped air. Balance shows a reading at this instance, right? Explain how you would use the reading of balance to estimate the pressure of trapped air. So let's say if the reading is M, right? Air pressure will be pi plus mg divided by A millimeter mercury, millimeter or centimeter, whatever. That much of millimeter mercury. Here, pi is the atmospheric pressure. G is gravitational acceleration. Gravitational acceleration. A is the cross-sectional area of piston. Cross-sectional area of piston. Next. When the piston was pushed to two different positions, the readings were recorded as follows. Piston's position, that's basically the volume of trapped air in milliliters, 18 and 10. So let's say this is V1, V2. Balance reading in kilograms, the weighing scale reading in kilograms, 0.6 and 3.6. State the law in physics that will be useful to you in determining the atmospheric pressure in this experiment. Boyle's law. Boyle's law. What is Boyle's law? Volume of constant mass of gas is proportionate to the pressure at constant temperature. At constant temperature. That's all they asked here. State the law. That's Boyle's law. Calculate the atmospheric pressure using the given data. If the cross-sectional area, I told you they have to give you the cross-sectional area, that's given. So we'll say P1 V1, P2 V2. P1 V1. Initially the reading is 0.6. So it will be pi plus 0.6 into 10 over 4 into 10 to the power minus 4. Right? Pressure. Volume in milliliters 18. Next time pressure, don't forget to add this, the atmospheric pressure. Whatever the pressure, additional pressure you are giving is on top of the atmospheric pressure. So pi plus, next time what's the reading? 3.6, is it? Yes. 3.6 over 4 into 10 to the power minus 4 into volume this time 3.6. Volume this time is not 3.6, it's 10. It's 10. Let's solve it. You will have, if you divide that 10 here, you have 1.8 pi. Bring that pi also here, minus pi equals, right? If I take 4 into 10 to the power minus 4 common base here, you will have 3.6 into 10. I forgot the 10 here. mg, right. So 10 is already taken, 3.6 into 10, 36 is here. Here you have 6, 1.8 is going to be a 6 into 1.8. Check that, check that. I took all the pi to one side. So when you cancel these two, 10 and 18, I can write it as 1.8. Now you have 1.8 pi here, and the pi from there, it's 1.8 minus 1 pi. 4 into 10 to the power minus 4 is common. Here you have 36. Here you have 6 into 1.8. So this is 0.8 pi equals, this is 10.8. 1.8 into 6 is 10.8. 36 minus 10.8 is 25.2 over 4 into 10 to the power minus 4. That will be, let's see if I can divide that by 4. If you divide that by 4, 6.3. So now if you divide by 0.8, it's going to be minus 4 going up. So let's say 63 or 6.3 into 10 to the power 4 divided by 0.8, which is 63 by 8, 56, 70, 64, 7.8, 60, 7.875, is it? 7.875 into 10 to the power 4 Newton meter minus 2. That's the pressure we are getting in this question, right? Atmospheric pressure, that's what we are getting. Approximately, you can take it as 7.9 into 10 to the power 4 or 7.875 into 10 to the power 4 Newton meter squared. Now they are asking, calculate the volume of trapped air when the reading of the balance is 0. That means only atmospheric pressure is given. So again you have to see, let's write this way. P1 V1, this time let me say P3 V3. This time the pressure is atmospheric pressure only. P1 pi plus this. The answer for pi you have got is 7.875 into 10 to the power 4 plus, right, the pressure P1 we had an additional reading in the balance 0.6 into 10 to 10 to the power minus 4, just 6 over 4 10 to the power minus 4 will go up into volume. How much was the volume there? 1.8 or 18 equals P3 7.875 into 10 to the power 4 only the atmospheric pressure is there, only the atmospheric pressure into volume is what they are asking, right? Let's solve it carefully. This is going to be 1.5, isn't it? 6 by 4 is 1.5. So 7.875 plus 1.5 means that is 9.375 into 10 to the power 4 into 18. 7.875 into 10 to the power 4 V3. 10 to the power 4 can be cancelled both sides. V3 will be, we have to multiply this by 18. Right? 18. I can approximate it to 9.4 into 18 over 7.9, isn't it? Quite a close approximation it will be. Then 9.4 into 18, that is 18 into 4 is 72. 7 balance, 18 into 9 is 162, 169 divided by 79. So you get 1, no, not 1, 2. 2 will be 158, 112, that's 1. 79, Subtract it. 33. 330. That's around 4. 21.4. 21.4. So look at the answer. We get V3 will be 21.4 milliliters. Go back and see here. When it was 0.6, it was 18 milliliters. Now this has become to 0. So obviously when the pressure reduces, this has to increase. It has to be more than 18. So if we solve it properly, it has to be more than 18. Yes, we are getting more than 18. What's the answer we got? We got 21.4 milliliters. Clear? The last one. So basically, same concept we are applying. PV equals constant. P1 V1 equals P2 V2. P1 V1 equals P3 V3. Right? Next. The trapped air pressure in this experiment is measured for values above the atmospheric pressure only, because you are pressing it. You are pressing it. Then only the scale will show the reading. Draw a diagram and briefly explain how this experiment can be done using the same cylinder for a lower pressure than the atmospheric pressure. Basically, you have to pull the piston up. If you pull the piston only, then the volume expands and pressure drops. How do we do that? Because when you are pulling it, the table scale or the table balance will not show you the force with which you are pulling it up. How are we going to do that? We'll keep it upside down. Look at this. The piston or the cylinder. Then you have the piston. Right. Now what you do, we will put weight here. This is where we are going to put weight. So when you put the weight, it will be pulled down. Then here what we will do, we will hang this on a spring scale, weighing scale, hanging scale. Try, repeat, I'll draw it again. Look at this clearly. We will take a scale. What is this? This is a what is this? This is a weighing scale, spring scale. On this, now what you do? Hang your piston. Hang your piston. Right. Then that's why you have to hang your cylinder. Now this is your piston. Look at this carefully. That's your piston. Now when you pull this piston, this will show you a reading, right? So that will show you with how much of force you are pulling it out. Right? How are you going to pull it? If you just manually pull it, then you can't keep it at a constant level. So what we will do, we will have an arrangement to hang some weight here. This is where you are going to keep some weight. Then when the weight pulls it, the pressure will reduce. The pressure inside, the trapped air's pressure will be lower than the atmospheric pressure. Right? So here we can say, let's say, tray, add different weights to the tray. And get the readings of readings. Let's say the readings are M spring scale. Now the pressure will be pi minus mgOA, centimeter mercury or millimeter mercury. Pi minus mgOA, because you are pulling it out. Earlier you were compressing, pressure increases. You pull it out, you give more space, volume increases and the pressure drops. Right? This is how we can do the same experiment. So this is, you can think like you don't necessarily have to have everything in the book. So I told you every experiment question or most of the experiment questions, the last part usually they give for you to think a little practically. So you have to use your common sense here and think, okay, they are talking about pressure less than atmospheric pressure. When I am compressing, pressure increases. So how do I get lower pressure? I should be able to pull it. What's the problem pulling it now? When I pull it, like in the diagram that they have given, where is our, in this one, if I pull it up, the scale, weighing scale will not show me any readings. So I need to get the reading as well. What shall we do? Keep it upside down like I have shown here. Keep it upside down and pull it here. Then your scale will show, your spring scale will show you the readings, which will be the force. Clear? So that is a nice question from Boyle's law. But two questions, both are from very old past papers, 1980 and 1981. Just study them, practice them. Let's meet up with another experiment.